somewhat related to the Green-Schwarz B field, but it has some extra terms, as you'll see. So the fact that the B field is antisymmetric in worldsheet derivatives means that you can write it in a way which is independent of the worldsheet metric, and of course the BRST trivial term is independent of everything. So it's a topological action. So the rules for computing amplitudes with topological theories, well, some things are well understood, but certainly this topological action has not been studied. But the hope is that we can use this to actually show that the amplitudes that you compute just reproduce the usual Feynman diagram expansion of super Yang-Mills. So I'll give some evidence for that in this talk. So the first claim is that at zero radius, the topological action has the property that the worldsheet essentially decouples into different regions. So the claim is that the regions near the ADS boundary will describe the propagators of the Feynman diagrams using the same description as Twopoint did, where you have these ribbon diagrams for the propagators. And then the holes between the propagators will be regions of the worldsheet which are near the ADS horizon. So I'll give some evidence for this claim. And then the second part of the claim is that the B field, which is proportional to R squared, which is the square root of the Twopoint coupling, is just going to reproduce the cubic vertices of the super Yang-Mills Feynman diagrams. So of course, if these claims can be shown rigorously, then you have a proof of the Maldacena conjecture, because at least at small coupling, super Yang-Mills is of course described by the Feynman diagram expansion. So interrupt me if you want during the talk, if you have any questions. So of course there are many other related approaches to studying string theory, or ADS 5 times S5 at small radius. So the first, I guess, one of the earliest ideas was by Gopa, Kumar, and Waffer to study these closed open dualities in a simpler version of ADS 5 times S5 related to the conifold transition. So there you really have a topological string theory to describe the conifold transition, and that was made more rigorous by Oguri and Waffer. And then there was a related, also discussing closed open dualities by Gaiotti and Rastelli. So all of these papers, of course, one of the motivations is to try to understand the ADS 5 times S5 open-closed duality. And as you'll see, some of these ideas from these papers also appear in this work I'll discuss here. Okay, there are also some attempts to describe ADS 5 times S5, at least at zero coupling, as a topological string. There was an idea of Polyakov, and there were some papers I wrote maybe 10 years ago together with Kumar and Waffer and by myself about realizing the ADS 5 times S5 action as a topological action. Then, of course, at small coupling, you also can try to relate string theory with these string bits, which, of course, are useful if you want to discuss integrability at small super Yang-Mills coupling. So, of course, there's the original BMN paper, and then there are several other related papers, and the most recent by a group from Perimeter and Sao Paulo, trying to get the integrability description from some kind of string-like theory. Finally, of course, there's the twistor string by Whitson, and also there's some work, that I've had some discussions with Juan Maldacena about this. Of course, the twistor string describes super Yang-Mills, and one of the motivations that Whitson had for looking at this twistor string was really to describe ADS 5 times S5 at small coupling. Okay, so these are some related ideas. So the starting point here will be looking at half BPS vertex operators. The reason is because half BPS vertex operators, of course, are the simplest things to study in the string theory, and they're supposed to be independent of the radius. So if I understand the half BPS vertex operators at large radius, I also understand them in some sense at small radius. And then once we understand the structure of the half BPS vertex operators, at least at small radius, there'll be a natural conjecture for the full non-BPS, or the general non-BPS vertex operators. Okay, so this is going to involve a little bit of technical things for ADS 5 times S5. In some sense, if you already have seen this, it will be simple. If you haven't, probably you can't follow. But the idea is that you parameterize ADS 5 times S5. There are various ways to parameterize it. Probably the simplest way, or a simple way, is using a super coset of PSU24 over SO41 times SO5, which I've written in terms of these three cosets. So the F of theta is just a fermionic coset, so that just has thetas in it. So it's PS224 over the full bosonic part of PS224. And then Gx and H of y are just the cosets for ADS5 and S5, just the bosonic part. So of course this is a perfectly good parameterization of ADS5 times S5, and it's nice because it separates out the fermions from the bosons. So if you want, you can pull out the ADS5, so the usual 6 vector that you use to describe it, normalized 6 vector for ADS5 and S5, just you can write them in terms of these cosets using this Pauli 6 matrix, which I guess John in his talk called the metric, so the SO5 metric. Okay, so this is essentially straightforward. Now what you want to do is you want to describe the vertex operator. So in any supergravity background, the pure spinor vertex operators have this form where lambda left and lambda right are left moving and right moving, or covariant to left moving and right moving pure spinors. So they satisfy this pure spinor constraint where m goes from 0 to 9. So these, instead of having 16 independent degrees of freedom, each one only has 11 independent degrees of freedom. And this A alpha beta is a superfield which contains all the supergravity field. And its constraints to be BRST invariant. So in the pure spinor formalism, in addition to the Worldsheet action, you have a BRST operator. And the BRST operator is always written in this form, so it's the pure spinor times what looks like a constraint. So in Green-Schwarz language, this would be called the Green-Schwarz constraint. But here it's not the constraint, it's just a covariant derivative. So you have 32 covariant derivatives, 16 associated with, well, if you like in flat background, it would be associated with the left moving thetas. And in a flat background, R would be associated with the right moving. Of course, in ADS5 times S5, they're no longer left moving and right moving. But you can still keep that notation of L and R. And you can write explicitly these derivatives in terms of left invariant currents. So in the notation which is common for these PS224 invariant currents, so these J's, the J's take values in the Lie algebra PS224, and there are 32 fermionic generators, and those are what are called J1 and J3. So the bosonic ones are called J0 and J2. So again, this is just notation. If you've never seen it before, don't worry. But if you have, then of course you know what I'm talking about. And this eta is just the gamma 5 matrix, which will appear all the time in this construction. Okay, so of course you have to know how the supercoset transforms under BRST, and this is the transformation. So it's not so complicated. So G transforms under the global PS224 by action from the left, and it transforms under the local SO41 times SO5 by action on the right. But if you have a fermionic action from the right, so this is a fermionic action because it involves the Q's and not the SO5s, it's not of course it's not a gauge symmetry. But under this combination where the parameters are just the pure spinor ghosts, it's a global symmetry, and that's the BRST symmetry. So of course, we have to construct our vertex operator so that when you act with this BRST, the vertex operator is invariant. So what we'll find is a very nice solution of this, at least for the half PPS vertex operators. Okay, so as I mentioned, of course, you still have the SO41 times SO5 coset, and these pure spinors transform under these local SO41 times SO5 gauge transformations as SO41 times SO5 spinors. So they sit in the tangent space, so that's clear if you look at, I'm trying to go backwards. Okay, if you look here, it's clear that these constraints are in the tangent space, so this is of course M is 0 to 9. So the SO41 times SO5 tangent space spinors, and it's convenient to use G and H, the cosets G and H, to construct spinors which are not SO41 times SO5, but they're actually SO6 times SO4, SO4 2 times SO6 spinors. So of course, because we have these cosets, we can do that. So that's something special in ADS5 times S5. And these are nice because at least the fermions transform in a simple way with respect to these tilted spinors. So these are no longer pure spinors because although these lambdas are pure spinors, when you act with these cosets, they're no longer pure spinors. So of course, if you know what G and H is, you can work G and H and you know what lambda tilde is, then of course you can rewrite the pure spinors in terms of those objects. Okay, so this is the BRST transformation. And now one wants to write, so is there any questions? Go ahead and interrupt me. Okay, so now we want to write the half BPS vertex operators. So let's consider just this simple half BPS vertex operator with just one of the scalar fields. So of course one of the complex scalar fields, the trace of it to the nth power. So the phi j k are just the 6 scalars. So j and k of course go from 1 to 4, and this is antisymmetric in j and k. And y0 jk, that's just a 6 vector, but it's null. So it picks out complex scalar. And in addition, so x is the position of the scalar on the 4-dimensional boundary of ADS5. And it's convenient to also write x in terms of a 6 vector. So of course it's a null 6 vector because it's on the boundary, and this is just its expression in terms of the 4 vector xm. So this state of course carries dilatation number n, and it also carries U1 charge n, where the U1 is the U1 which of course phi has a phase with respect to that U1. So the choice of Y0 chooses a U1 out of the SO6. Okay, and this state is annihilated by 24 of the 32 supersymmetries. So it's annihilated by the ones which have J minus delta greater than or equal to 0. So there's 16 supersymmetries with J equals delta, and there are 8 more with J minus delta equals 1. Okay, the claim is that the corresponding half BPS vertex operator, which describes the state, is just given as follows. So, so lambda L, lambda R is this combination of the left and right moving ghost using the gamma 5, the same gamma 5 that, of course, is the Ramond flux. This y and x are just the usual S5 and ADS5 coordinates. And so this would be the bulk to boundary propagator if you're just thinking of the bosonic scalar bulk to boundary propagator. So it's written, of course, in SO4 2 times SO6 notation. And P is this object which I'm going to call a picture lowering operator for a reason that will become clear. So it's constructed from thetas and Q of thetas, where the thetas are chosen such that they're the thetas corresponding to the supersymmetries which are not preserved. So out of the 32 thetas, there are 8 thetas which carry J minus delta equals 1. And those are the ones which transform under the 8 supersymmetries which don't preserve the state. So if you want, you can write them explicitly in terms of x0 and y0. So x0 squared equals 0 and y0 squared equals 0. So this combination, although it looks like there are 32 independent thetas here. So remember, I'm sorry, I should have reminded you. So theta, of course, there are 32 thetas, and 16 of them sit in the left diagonal or top left, and the others sit in the bottom right diagonal. So I write these 16 of them with an upper, so K is the SU4 index and S is the SU22 index. So one of them, so half of them are of this type and the other half are of this type. So these, if you like, are the chiral and anti-chiral thetas. And if you contract with x0 and y0, then because x0 squared and y0 squared is 0, these 16 just reduce to 4. And these 16 also reduce to 4. So these 4 and 4 just give you the 8 thetas, which carry J minus delta equals 1. Okay, so the claim is that this object is BRST invariant. So before showing it's BRST invariant, we're going to, of course, show that it has the right charges. So, of course, this object here tells you that it has the right charges with respect to the U1J charge and the dilatation charge. And P, because it has this form, has no charges, because Q of theta, if you have a delta function, that just cancels the charges of theta. And lambda L lambda R is just PSU224 invariant. Okay, so this object is called a picture lowering operator because it has delta functions, which are related to the delta of these lambda tildes. Just like in the RNS formalism, the picture lowering operator has things like delta of gamma, where gamma is the chiral boson coming from fermionizing the beta gamma system. So you can get the vertex operator in the usual 0 picture, the one which just has lambdas and not deltas of lambdas, by hitting with something which is going to be called a picture raising operator. So I'll call this C. So just like in RNS, it's constructed by hitting with Q with C, where C is the conjugate to the eta, which appears in the beta gamma ghosts. You can think of this as being the picture-raising operator in this pure spinor formalism, where this C is just the conjugate to the eta which appears in the lambda tilde. So you can also write it in terms of the Heaviside function, or the theta function. I guess, what is it called? Heaviside function? Of a conjugate to lambda tilde. Okay? So this is, of course, formal, but let me show how it works, at least in a flat background. So the claim is this can also be done in a flat background for the usual type 2b supergravity vertex operator. So let me just say how that works. So usually when you write supergravity in string theory, you write it as the left-right product of open string vertex operators. But in type 2b, you can do something slightly different. You can try to write the vertex operator in terms of the chiral superfield. So this is the chiral superfield whose lowest component is the dilaton plus I times the axion, satisfies these constraints here, where d minus is just, it's a combination of the left and right moving thetas. Okay? So this is not usual in string theory, but of course there's nothing stopping you from writing the vertex operator in terms of the chiral superfield. And it turns out to have this very simple form. So it's written just as the sum of terms, where these del plus are the covariant derivatives which don't annihilate phi. And it's contracted with different combinations of these lambdas. So the claim is this is a BRST invariant expression if you add these four terms. And now if you consider just the vertex operator for the lowest component, which would just be the dilaton psi the axion, you can write that in a simple form using this picture changing operator, where it's exactly the same form as. So P is this combination of the thetas which the supersymmetries which don't annihilate the dilaton plus I the axion. So you can just write it in this simple form. So this is supposed to be equivalent to this. And C has the same form as before, and at least in a flat background it's very simple to work out these products here. So the trick is that just like in the RNS formalism, when you have a xi and you multiply it by a delta function of gamma, you can replace this by xi times e to the minus phi. So e to the minus phi, using Friedman-Martinek-Schenker notation, is related to delta of gamma. So this combination here is just 1 over gamma, because gamma is a to e to the phi, 1 over lambda, because lambda is a to e to the phi. So everywhere you multiply a c times a p, you always can contract these x's with delta of lambdas, and you get these 1 over lambdas. And then you might be worried that the final expression is not going to be a polynomial in lambda, but you can show that if the original expression is BRST invariant, all these poles in lambda are absent. So this construction here is just a simple way of writing this vertex operator. So in ADS5 times S5, this expression will be much more complicated, but at least this expression is still just as simple. Okay, so that's the trick we're going to use for the half BPS vertex operators. And now the question is if we can generalize this to the non-BPS. So of course, if we want to try to discuss the correspondence, we have to do non-BPS also. And the trick is, instead of just having one picture raising and one picture lowering operator, we're going to just write the vertex operator in this way, where it's the product of n picture raising and n picture lowering. So of course, because if you add an equal number of picture raising and picture lowering operators, it's a BRST operation. This V is in the same cohomology as before. And now you see that it has the form of something like a spin chain. So its small coupling, of course, super Yang-Mills states can be described by spin chains of just the spin fields in the gauge invariant operator. And this naturally looks like something of that form, where this P y dot y0 over x dot x0, you can think of as being the Yang-Mills scalar associated with this state here. Okay, but now the idea is, if you want to do general non-BPS, you just replace these by the appropriate super Yang-Mills field. So instead of choosing them to be the same scalar, you can choose them to be different scalars or fermions or anything you want, where these E's are just obtained by acting on these objects here by the appropriate PSU224 transformation. Okay, so the conjecture is that if you suitably define normal ordering, so of course you want normal ordering to preserve this cyclic property so that this can be interpreted like a spin chain, then the conjecture is that the non-BPS vertex operators, at least at small radius, can be written in this form. Okay, so this is going to be This is, I guess, the first conjecture. Okay, so it seems like a reasonable conjecture. Okay, so now what we want to do is we want to understand how this is related to free super Yang-Mills. Okay, so it turns out that lambda tilde, as I mentioned, is related to the pure spinors, but it also involves G and H, these ADS5 and S5 cosets. And it turns out that the 8 lambda tildes that we're going to choose to write the delta functions in terms of these lambda tildes are all proportional to square root of z, where z is the distance to the boundary. So z equals 0 means you're on the ADS boundary, and z equals infinity would be near the horizon. So because the vertex operators, or the terms e's in the vertex operator, are proportional to delta of lambda tilde, so that just comes from the picture lowering operator here. P, remember, is proportional to delta lambda tilde. Then at least these e's will all have to be near the boundary. Furthermore, c's involve this Heaviside function of W tilde, which means that lambda tilde will have poles here. So that means that the z's are going to be near the horizon when you're at these points C. So if you do a normal ordering where you think of these C's and E's as being cyclically distributed around a string, a small string, then the point is that the worldsheet is going to be near the boundary at these E locations and near the horizon at these C locations. Okay? So the second conjecture is that in the presence of these vertex operators, the worldsheet is going to split up into regions which are near the ADS boundary and near the ADS horizon. Okay, so let me draw a picture just. So let's just consider trace phi squared, just to be simple. So you'll have, these would be the E's, and then you could have these C's would be here. So these would be near the boundary, and these would be near the boundary, and these would be near the horizon. Now suppose you want to compute an amplitude. So suppose I have 2 of these states. So you're going to have a cylinder now. So let's just do the 2-point function. So you're going to have a cylinder where the idea is that the cylinder is going to split up into regions which are near the boundary and regions which are near the horizon. So you'll have 2 regions near the boundary and 2 regions near the horizon. So the claim is that it splits up in that way, and let me try to give some evidence for that. Yep. So the sigma i's you can think of as the coordinate around. So this would be at sigma 1, sigma 2, sigma 3, sigma 4. So there'd be, if you have a cylinder, you can just think of it as the sigma parameter of the cylinder.
So in defining this vertex operator, are you taking, presumably you're taking limit when they are all approaching the origin?
Yeah. So there's this, of course, if this is a topological string, so you can ask, well, what's the size of the hole here? But these are good questions, but let me leave them for the end, because that is an obvious question. Yeah. Okay, so something about this topological action, which will help to justify this description. Okay, so at arbitrary radius, at arbitrary radius, you can write, of course, this is the usual ADS 5 times S5 worldsheet action. In the pure spinor formalism, there are ghost terms here. In Green-Schwarz, these have the same coefficient, or opposite coefficients, but in pure spinor, there's a symmetric part here, too, which allows you to define propagators for the fermions. So, of course, BRC symmetry and not kappa symmetry. And the claim is you can write this action, at least formally, as the sum of a BRC trivial term and an antisymmetric term, where the antisymmetric term, this is the usual Green-Schwarz West-Semino term, but then there's some other terms also that are added. And Q of psi contains all the terms of here which are symmetric in Z and Z bar. So it contains the usual term for the x's. It also contains terms for the fermions, etc. And psi, okay, you can construct. It's a bit of a mess. It contains inverse powers of this lambda left, lambda right that you might worry about. So it's a formal expression, but okay, you can write this down. Okay, now, because this is a topological term here, this is BRST trivial term, the coefficient in front of the BRST trivial term is arbitrary. So we can make lambda as large as we want. And if we make capital lambda large, then you can see that this term is going to freeze x to be at 0 modes unless z is equal to infinity. So if z is finite, then as you make lambda large, this will have to vanish. So x will be reduced to the 0 modes. So x is essentially frozen unless z goes to infinity. So you can think of z going to infinity as being the regions where x can be discontinuous. So that's the description here. Here you have, in these regions here, x is constant. But then you can have some discontinuities from here to here. So you have two distinct regions here, where this would be the region near the horizon. Okay, so that's this picture about the worldsheet splitting up into different regions. And now the claim is that each of these regions containing these Yang-Mills fields E precisely have to contain two Yang-Mills fields. So let me give you the argument for that. Okay, so as I mentioned, the worldsheet is going to split up into the regions which are separated by discontinuities, and the discontinuities are precisely where the worldsheet is near the horizon.
So in your notation, horizon corresponds to Z equal to P.
Yeah, or Z very large.
Z very large. So that corresponds to even Z?
So that's, so I don't remember what I did on the, yes, so in this language it would be the even ones.
So X can vary around even Z?
Yeah, so here X can be discontinuous. So you can think of this as being like a D3 brane. So the X's in the D3 brane can vary. So it's not dissimilar to what you did with Qumran, where the holes are some fixed, some different regions in the. Okay, other question? So I didn't mention that, but of course there are also 16 thetas which can become discontinuous here, also because of the D3 brane. So the ones which carry positive dilatation weight can be discontinuous near the horizon.
I think a picture of the string is like a folded string with length and boundary, and it's a closed string, but it's folded this way.
So I'm thinking of it like, let's just do a cylinder first.
The string, the physical string.
Yeah, so the string is this circle here, and it's split up into folded. I guess, yeah, okay.
It gets folded, and
Okay.
most of it is inside, but there are 2 points on the boundary.
I would say it the other way around, but okay, so I would say it's discontinuous at 2 points. So you should probably think of the boundary as being bigger than the horizon. The horizon, so most of it is on the boundary, so you have thickened propagators, but you have discontinuities here. So it splits up into like what people call string bits. Okay, so the claim is that in each region, you have to have precisely 2 of these. So you could have asked, well, why can't I have more? Why can't these boundaries have more than 2? Why do they just connect 2 of these E's? And the claim is that it vanishes unless you have precisely 2 E's. It's just by theta 0 mode counting. So the claim is that each of these regions contribute precisely the propagator super Yang-Mills to the amplitude. So the integration, of course, you have to integrate over the 0 modes which survive. And the claim is if you do that integration, you're just going to reproduce the usual super Yang-Mills propagator. And of course, for non-planar diagrams, you're going to have also the contribution coming from the string coupling constant. And that's going to give you the usual end dependence. Okay, so the description, of course, is the same description as 't Hooft, but now it's made more explicit, where you think of the propagators as coming from the regions near the boundary, and the holes as the region near the horizon. Okay, so this is free super Yangmills. So if you swallow that much, then we can try to do the interactions. Okay, so the idea is now, if we want to do interactions, so let's suppose we have 3 of these states. So each of them have propagators going like this. So this would be trace phi if we have 3 of these. So this would be what the worldsheet looks like. And now, so I guess I want to compute this. Now suppose we want to introduce interactions. So this is just free super Yangmills. If we want to introduce interactions,
So before going to the 3-point function, can you look at the anomalous dimension, which would just be a 2-point function? I mean, like the one.
so this is just free super Yangmills. There's no anomalous dimensions. So it would just give you the usual classical dimension of the fields. Yes. So before I turn on the B field, it's just R equals 0. Yeah, G string is, that's right. So G string is just the genus. So it's a topological string at a different genus. You have what? That's a good question. So all of the fields are, so the spectrum is just free super Yangmills spectrum. I mean the spin chains of the free super Yangmills. Yes. So they're just constructed from so the spin chain just has, it's just a chain of arbitrary super Yangmills fields. So the spectrum is well known for free super. Maybe let's wait for the discussion. Okay, but the picture is okay? So for free super Yangmills? The number of E's? Yes. Yes, so it's free, so that's right. So now if we want to do interactions perturbatively, what we want to do is we want to have a loop here. So we want to allow something like this. So this would be an interaction term. Okay, so we have 2 cubic vertices. We have a cubic vertex here and a cubic vertex here. Okay, so this would be the terms we want to introduce in order to introduce interactions. So the claim is these terms here are going to come from 2 powers of this B field. Okay, so each vertex is of course proportional to R squared because it's square root of 't Hooft coupling. So the claim is that every time you drop down a factor of R squared D squared tau B, you're going to introduce a vertex into these diagrams. Okay, so let's see how that can happen. So first of all, Yangmills normally is written as a quartic action, but of course you can write it as a cubic action by introducing auxiliary field. So here's the cubic action. And then the claim is that the B field is just going to introduce these cubic terms. Okay, so the B field, as I mentioned, it contains the Green-Schwarz term, but it contains some additional terms related to the pure spinor ghosts. So you can work those out. It just comes by analyzing the structure of the BRST trivial term. Now the claim is that these terms which are antisymmetric in Z and Z bar get turned into commutators in the super Yangmills action. So that's, of course, something similar happens in this supermembrane matrix theory description. So the claim is that the terms J1 wedge J3, so if you write these in terms of the x's and thetas, at least if you do an expansion, then you have terms of this type. And the claim is this term here is going to be related to this cubic term in the super Yangmills vertex. And this term here is going to be related to the bosonic term. Okay, so let me give some evidence for that. So the idea, so here's a typical term in the B field, so it's antisymmetric, and so tau and sigma are my two worldsheet coordinates. So if I think of dividing up my worldsheet into very small squares, then of course on one of these squares I can write this in this form here. And now we're going to think of the square as being a small spin chain, where the corners of the squares are just the four elements of the spin chain. And now if you just write these terms in terms of where they sit on the square, you see that they just reassemble into something where you have first F. So you have, on one term it would be F here, G here, and H here. And on the other term it would be F and then H and then G. So it reproduces exactly the commutator that you want of a spin chain. So it's a spin chain where in one term it's FGH and on the other one it's FHG. So the claim is that these terms in the B field reassemble in that way. So one way to see how that works, okay, so here's the term that I mentioned that comes from the J1 wedge J3. So this looks like a spin chain where you have theta, x, and theta at the three different points on the spin chain. And now the claim is that this is going to reproduce the term in the cubic super Yang-Mills action with two gluinos and one gluon. So the way to see that is you can think of to compute the contribution of the B field, you can think of computing the closed open amplitude. So we can have an amplitude with so now I'm on a disk, and I can think of the closed state. So the B field would be the closed vertex operator on the disk, and then you have some open string vertex operators at the boundary of the disk. And now one can try to compute this amplitude in the topological theory, and the claim is this amplitude here is going to tell you precisely the contribution of the B field to the Yang-Mills vertex. And now if you use the form of the open string vertex operator, so this is the usual open string vertex operator in the pure spinor formalism. So this is in a flat background, but in other backgrounds it's related. You can see that the theta is going to be dual to this D, or conjugate to the D. The X is of course conjugate to the DX. So you can see precisely how this term here is going to reproduce this cubic vertex if you compute the OPEs of these V's with this B. And similarly for the bosonic term. So in the bosonic term here, the thing that's slightly strange is you have this constructed from the pure spinors, but in the vertex operator for the open string, the field strength couples precisely to the Lorentz current for the pure spinors. So that's going to turn this into just F. So this term here is going to reproduce the usual bosonic term in the cubic vertex. Okay, there are other terms in the B field that I haven't mentioned, and okay, there's a conjecture, of course, that they don't contribute. This, of course, I mean, all of this needs to be done much more carefully. This is just hand-waving, but at least the hand-waving seems to suggest that the B field does indeed reproduce the cubic vertex. And in fact, it's hard to see how it could give something different, just because the B field is, of course, PS4 invariant, and the cubic super Yang-Mills vertex is essentially the only thing you can write down, which is PS24 covariant in the Yang-Mills language. So if it gives a piece of it, it has to give everything. Okay, so of course these are conjectures, but hopefully if you understand better how to do computations here, you can make the conjectures more rigorous. Okay, so the arguments that I sketched here were that, okay, firstly that there's a topological string action that describes ADS 5 times S5, at least its small radius, and the propagators, so the regions of the worldsheet which are near the boundary describe the propagators of super Yang-Mills. The regions near the horizon describe the holes, and that the cubic vertex is described by this B field. Okay, so there are, of course, many open questions. So, of course, one needs to understand better how to do amplitude prescriptions for this topological string. I think the technology of topological string theory is well developed, but certainly I'm not one of the people who knows it well. So hopefully this can be done more rigorously. One has these factors of 1 over lambda left, lambda right, which appear in this description, which you should worry about, I worry about, but at least I hope that it seems that things can be done. They're not different from the non-minimal variables which appear in, for people who know the non-minimal pure spinofluence. You also have factors of this type, and hopefully they're not going to be obstacles. Another question is, this topological string theory doesn't have any worldsheet moduli. So as usual in topological strings, there's no dependence on the worldsheet metric, so you don't need to integrate over the worldsheet moduli, you integrate over Teichmuller parameters. So of course in the usual string theory you do. So there's an obvious question, well, how do you relate the two? So in this description, you just have Feynman diagrams and propagators, but you don't have any integration over the Teichmuller parameters. And a question is, of course, how to relate this to the usual string description. Okay, so let me stop there. Yes. Yeah. So so if you have a theory which is independent of the worldsheet metric, so the vertex operators, if you try to change the location, it's just a BRST trivial operation. So the difference, so let me say a difference between, okay, so you know the topological strings much better than me. So,
For 3 point, yes. For 3 points there is no moduli.
So,
4 points?
so usually the question is what you can write down which is non-vanishing. So for ghost number counting, normally in order to get something non-vanishing, you need to have, some of the vertex operators have to have 0 ghost number. In this description, the ghosts are bosonic. So if you allow things like 1 over lambda left, lambda right, then in some sense the ghost number is ambiguous. So the distinction between integrated and unintegrated, so let me give an example which is actually related to this last transparency I had. So you have this operator d squared tau b, so that's of course has no ghost number. But the unintegrated vertex operator associated with this is just lambda left, lambda right. So if you just use the usual descent procedure, the lambda left, lambda right is the unintegrated vertex operator for the radius modulus. So if you allow things of this type, then essentially you're saying that the number of unintegrated versus integrated vertex operators is arbitrary because I can just divide by ghost number. So at least you're allowed, if you're allowed to divide by this, then I can have an arbitrary number of unintegrated vertex operators and compute something non-vanishing. So, and okay, for higher genus, again, there's no need to integrate over the Teichmuller parameters because, well, any deformation of the worldsheet metric is BRST trivial. It doesn't affect. So, it fits with the description you want in the sense that you're already reproducing the Feynman diagrams. There's no. Yes.
You obtain string amplitude, 4-point amplitude without integrating over.
Yes. So it's just a Feynman diagram. So you get the Feynman diagrams without integrating over the. So usually you get Feynman diagrams by integrating over the positions of the worldsheet. But in this case you don't. You just get it. It's just sewing together propagators and vertices.
So there are no renormalization theorems in any of the Yangmills two-point function, triple function of the Maldacena Conjecture are not corrected by.
Yes.
Do you have any idea of how to do it in this approach? So that means if you insert this B, it shouldn't result.
So I haven't thought about, so at the moment I'm just trying to reproduce the Feynman diagrams. If you're asking if something new can be obtained by.
So you say that we reproduce precisely Feynman
Yeah.
diagrams, no renormalization theorems should be.
The same like the Feynman diagram. Is there anything you could prove using Feynman diagrams, could prove using this. Assuming that this reproduces the Feynman diagram. So, Arkady, you had a question. I can come back to it if you want.
Yeah, my question
So, yeah, so I don't know who the first one to show this is, but I mean, I've heard Polyakov associated with it, but I mean, all of the states of, so you just have I mean, I'm writing the gauge field, but it could be any of the scalars or fermions. And I think what you're asking about higher spin symmetry is a statement that on each of these states you can act with PS224 independently. So the spectrum of this, I mean the mass spectrum of this is independent of, I mean, so the dimension of AM is 1, independent of the other states. So, I mean, the symmetry acts independently on each of these. Essentially, they don't interact for the free super Yangmills. So I don't think there's anything more to say about the spectrum than just this. I think this completely describes the free super Yangmill spectrum. Yes. Yeah, so I can tell you the dimension of all of these states. It's just the sum of the dimensions of all of these operators. So you're asking how to compute the energy of the topological string and show that it reproduces this. Okay, so the claim is that in this topological string, these essentially decouple. And so the dimension would just be the sum of the dimensions of each of these. Okay, let me show you the vertex operator. Sure. Okay. Good idea.
Vuoi l'annuncio mentre io faccio questo?